We have two presentations and commentators today, so we have to try to keep things bounded, so to speak, in order to leave time for questions. I'm going to try and time my talk between 25 and 30 minutes, and then Juan, my co-author, Jacobo, is going to talk for a few minutes, and then we're going to switch to Paulo. Okay. So the question I want to address is the question of income levels and income distributions. Now we know that per capita income rises over time, and that there's a difference between pre-tax and post-tax distributions, and I'm concerned here, we're concerned here, with the pre-tax because that's what the market gives you. So this is an explanation of the market outcomes, not the social intervention. And that's for one reason why the outcomes are similar in the United States and Sweden, pre-tax. And when you look at the income sources, you have wages and salaries, you have property incomes, and wages and salaries are concentrated in the bottom 97%, we'll show you that, and property incomes in the top 3. Now of course, there's a kind of gradation. You get property incomes rising as your wage income rises, but it really jumps at the top because those are people who are essentially living on property income. In any time you think that you're in the upper class, just realize not in income, definitely, or wealth. Otherwise you wouldn't be here. Or you are, talk to me because I would like to get to know you better. So the question is, what about the distributions themselves? What's driving it and what could account for these differences? Well, we have 3 kinds of stories. Neoclassical theory, which is marginal productivity and of labor and capital. Your wage is what you are worth, what the market deems you're worth. So except in the admission of some discrimination, basically incomes are based by your contribution of some sort to the firms who employ you. In classical theory, the story is told completely differently. It's about social struggles between capitalists and workers, and struggle among workers and struggle among firms and firms. So it's a story of power bounded by the laws of competition. And that's the point I want to pick up. What influence does the laws of competition have on this process? And then in the physics theory, the argument of the people who sort of developed econophysics is that this is energy conservation, or the equivalent of it in economics is money conservation. So because by the laws of energy conservation, we have a lot of tools, and if you just transpose them into money, you get results that look very similar to the observed ones. I'm going to concentrate on my presentation in the difference between the physics version of econophysics and what I'm calling the classical economics version of econophysics. So let me start with Pareto. Pareto did many things. By the way, you should read his biography in Wikipedia, which I looked up again recently. He was really conservative and nasty guy. But one of the things he did is he fitted data to a variety of income sources. Now remember, in those days, workers were not taxed. So income sources tend to be biased heavily towards those who were taxed, which is, of course, the upper classes and maybe merchants and so on, but not really labor income. And he found that at least for the top parts, there is a pattern, which he observed in many different countries. And he found by graphing it in a certain way, the pattern always appeared, and that was a straight line. And that's what we call a Pareto Law. And I'm going to show you that different. It turned out that it wasn't useful to graphing, to dealing with incomes of wages, because as capitalism developed and we get to tax more and more people, and we have information on more and more people in order to be taxing you, it didn't work. So what the physicist Yakovenko and his co-authors discovered or argued is that the distribution really has 2 components, coming from wage income and property income. And they call it 2-class theory. Now, you know, when I see something called 2-class theory, they can explain things, I'm immediately attracted to it. So I pursued it more. I asked Victor, by the way, how did you come up with this idea that there are 2 different sources of income? And he said, are you kidding? I was educated in Russia. I know all about capitalism. So it was a natural thing for him. Now, we're going to use some tools. You're familiar with the idea of frequency. I'm sure. And cumulative frequency is just adding up the frequencies from the bottom, and cumulative from the top is reversing that and adding them up from the top going down. So at the top is 100% then, and so they represent different ways to display any given distribution. So this is the data for the frequency distribution in 2011 from IRS. You can, every year is the same, by the way. I'm going to show you that at some part of it. And it's not very useful to see a pattern here. And what the physicists say is, okay, you've got here frequency and here you've got income. But what if you take cumulative frequency and you plot it as a log? So here is the same thing, but it's a cumulative frequency as a log. And here's income. And you can see the first part is kind of a straight line. And the second part, which is not many points, by the way, 7 points, is a curve. And doing that, they did it because they know that the signature of different patterns are different on this kind of graph. And so we see, if we move this graph, we expand this part out. This, by the way, is roughly 200,000. So the bin from 0 to 200,000 is where the bulk of the population, and then you have these 7 points from 200,000 to 8 million. So if we take that and we just expand it out, you notice something really striking. This is the cumulative probability from above on a log scale. This is on a linear scale, just the income. And you're looking at the bottom part, under 200,000, and you see this incredibly powerful straight line. Now, when a physicist sees this, or a mathematician or statistician sees this kind of line, we know it's an exponential. Because the exponential, the log of the cumulative probability from above versus the level of the variable, is a straight line. And this is a signature, which it's easy to show is all years in the United States and different advanced countries, and subgroups that I'm going to show you for females and males, white and non-white, have the same pattern. Now for me this is very striking, but of course I have to try to explain it from the point of view of an economic explanation, and for me the foundation is classical economics. This is data for all incomes taken from the CPS. CPS is top coded, so it cuts off at 200,000. So it can only show the labor part. It can't show you the upper part, because if you could see that, you'd know who's who, and so they literally don't let you see that. But this is all different years from 1996 to 2007, and you can see that in different years, this is a straight line. It's different because the average income level changes. And in fact, if you normalize this data by dividing each year by the average income level, then all these points fall on the same straight line. And that's the beauty of an exponential. It's, and it's parameter free, by the way. And this holds for large amounts of data. Now what very much surprised us, and I don't know if Noe's here, but Noe Wiener and I and another student who did this for race, for gender, and I'm sorry, for race, and we were very surprised to find out that the patterns are the same. The levels are not. We know that. That's well established. But the patterns are remarkably the same. And then it raises a question. How could discrimination raise the levels and not change the patterns? And I'm going to try to make an argument to explain that. Now here's males versus females. Again, well-known problem of discrimination, or at least of differences, which we now interpret discrimination. Before, or in neoclassical theory, they interpreted as difference in quality. But regardless, this is a very powerful, and I was very surprised by that, by the way, when we found it, because I didn't expect that. Now let's look at the other part of the scale. Remember the original scale. This part is a curve when you have a log of income, log of cumulative probability versus income. But what if we put a log on the bottom scale? That double log form is this. And here again you find a straight line. This is called the power law. This is what Pareto originally found for the top incomes. Now this top incomes are roughly 3% of the income. 97 is in the bottom part. And so the question I want to pose, which Yakovenko posed, this is data for different years. The red line and the black line are different years. And I'm going to skip that in the interest of time. This is the power law for different years. You can see that the straight line form obtains. So how do you explain this? The physicists say, well, an exponential is what you get when you look at particles interacting with each other, holding energy constant in closed containers so they cannot leak, so to speak. And then you get a distribution of energy, which is exponential. So they basically adapt that notion. The steady state distribution will be exponential. They adapt that to the notion of interaction between economic agents. Now, in order to do that, you have to model the interaction that each economic agent bumps into another and gives them a packet. In this case, it's an amount of money. So they get less and the other gets more. That's an energy exchange in physics. It's a money exchange of people. And then they show that if you do this randomly, interacting each other, you get an exponential distribution of money holdings. Now, Yakovenko and all admit that there's no reason from this argument that these would be true for wage holdings. Because wage does not involve people bumping into each other and giving money. They involve a whole process in the classical tradition, especially of wages coming in and a product, surplus product being created and all of that. So how do you get to that argument from the econophysics argument? Now, many various models of this are in the paper, but I'm going to skip that. Then you come to property incomes. Obviously, this energy conservation principle directly in property incomes will not work because you won't get a power law. But it's what Yakovenko and his co-authors call superthermal. That is a type of interaction in which you can get a power law. And there are different ways. You can get power tail for higher incomes if agents are assigned savings rates drawn from a uniform distribution. Or you treat individual incomes as a stochastic process and then assume power law if income changes are proportional to the income level. So that's a multiplicative diffusion. Now these are all parallels to existing physical models. And my concern is, I was very impressed with Yakovenko data. And the question is, how do we understand that? So I want to argue that economists have a principle also, which is the equivalent of the classical idea, of the physical idea of energy conservation. Only in our case, it's not a conservation, it's a drift and diffusion process. So if incomes are higher here, wage incomes are higher here, we're talking now wage incomes, and lower here, then people would start to drift in that direction. So that idea, we abstract from all the obstacles along the way, will lead to equal wages. This is Adam Smith's proposition that wages will be equalized because people will go to the higher income, higher wage area. They'll increase the supply relative to demand. They'll bring the wage down. Here, a shortage of labor will decrease supply relative to demand. The wages will come up. And the only point where there's no further movement, and hence a balance point, is when wages are equal. So that's at an abstract level. But Smith, Marx, Ricardo all point out that that's at a high level of abstraction because they observe around them that this is not the case. And they point out that there are many factors that intervene at a concrete level. And one of the things we have to do is account for those factors. And the simplest way to account for them is to say that they are sort of random effects on individuals. They're random because we don't know the details. We know lots of details end up as a random thing in the aggregate. So this is a way of accounting for that. And that's called diffusion. So we have two things that are coming from Adam Smith. Drift, wages moving that way, and diffusion because there are many things intervene, including things that make you turn back and you fail or you get stuck in the middle or whatever. Or when you get there, they're not what you think. Oops, that is totally screwed up. I don't know what happened here. Let me see if I can fix that. It's because Well, that I don't know what to do about because what happened there? Okay, I'm going to have to, I have no idea what this is all about. Up. It's font, but it wasn't on my computer, so obviously, never mind. Let me just describe this to you. So we're proposing two models of the adjustment of wages to a difference among the individual wage and the mean. We normalize wages by the mean because that takes out the trend. So we're concerned with the distribution around the mean, which is what you're observing in any given year, because in any given year, the mean is given to you. So we're concerned with the spread around that. And so this is one in which the change in the log, which is roughly the change, a percentage change, is a function of the difference between the wage and the mean being normalized to 1. And if the wage is above that, pressures will come to bring you back. That's the mobility of supply of labor that brings you back. And the last term is just an expression for noise, sigma times dw dt, so you have a noise term there. Now, we also have in the paper, which you cannot see amazingly, a second model in which we have the change in the log is minus here, instead of the level of the wage, the log of the wage, minus the log of 1. The log of 1 is 0. So therefore, this is minus sigma times the log of the wage, and the noise term is 0. And the reason we did that is that there's no a priori law, so to speak, to how to model or form on how to model wage movements, except that supply of labor moves to higher wages and that brings the wage down. And both of these model, and obviously many other models. But one important consideration in the wage story is that the model has to pick up the idea that the wage is positive. And if you define the wage relative to as an excess of a minimum wage, then it should be positive, meaning it's above the minimum wage. And this allows you to build that in automatically, because this gives you positive wages. So does the other form, which you can't see. So this is the empirical fit of these two wage models, log linear and log log. Both of them are mean reversion models. And the dotted line is the fit of the actual data, and the red dots are the fit of the log linear, and the little triangles are fit of the log log. And you can see that these models give a very good fit to the actual data. And Juan is going to talk a little bit about the math and the technique of simulation and all of that. But we can derive the stationary distributions from the model itself. Now, why did this? I don't know. This is the same thing, only now we have to talk about property income. And the thing about property income, which I'm defining as pi, is that it's the product of a rate of return and the amount of assets per person. Your portfolio times your rate of return, that's it, property income. And again, the same principle applies. If the rate of return is different in two areas, capital will move to the higher rate of return, bring it down, move away from the lower rate, bring it up. But if we allow for diffusion, you're going to get some distribution. And the question is, what is that distribution going to be? Here we have two models. Again, the first one corresponds to the same form as the labor model, only now it's the profit rate, or the rate of return, really interest rates, risk adjusted. And here is the log-log form. The change in the log of the variable is equal to minus sigma times the log of the variable, because the log of the variable minus the log of 1 is just the log of the variable. So the key question is, what determines the other term? Property income is rho times A is assets. So what is your theory of assets? And what we proposed, I've skipped over that in the part of the text, is a very simple proposition that if the rate of return on your assets are higher than the mean, the quantity of your assets will grow, either because you save more or because their market value will rise. We don't need to specify more than that. It's a very simple way of expressing what we know, that you get richer if you do well. So putting that story into here, which is simply dependent on the form in which you present the growing part, you get these two models. And these are the two property models, you notice that they're based on the same principle of arbitrage. And now this is the actual data for property income. And the red part is the log linear model, and the log part is the triangle is the log linear model. Now, since in the log linear model we're fitting the top 3%, which is where the data is, you have to constrain these models to the top 3. And the standard way is to use a reflecting barrier to keep everything in the top 3%, which is basically similar to a power law. So you get these fits, and these are completely general. They're true for every year. I'm showing you 2011, but they're true for every year, and because the data is the same for every year. Now, my friend Duncan is here, and he did an amazing paper, which he did originally in the department seminar. That's how we met. And he had, in his remarkable book, he has a completely different story that fits the same data. And I want to mention that because the point is that fitting the data alone doesn't give you the story. He assumes fully equalized wages. He's operating within neoclassical framework. Fully equalized wages and fully equalized rates of return for any given capital asset. And from this, his goal is to derive an ideal distribution of income in perfect capitalism. To do that, he begins by defining what he calls the effective utility from work, which he calls happiness, as the utility from pay minus the utility from effort plus the utility arising from a sense of fair opportunity. Giving specific forms to these three variables, he arrives at a central prediction that in a homogeneous population of agents with the same payoff preferences, can you see that? Sorry? I'm sorry, I can't hear that. What? Oh, microphone disconnected. Yeah, because it slipped down. Yes. No. Disconnected here. Okay, can you see it? So he assumes that a free market leads to individual maximization of happiness and hence to a fair distribution of income. That is a unique Nash equilibrium in a non-cooperative population game and an entropy maximizing state. And with these assumptions, if all individuals are of the same type or the same class, then you'll get a log normal distribution. But if there are two classes of agents with different payoffs, then you'll get two log normals, one for the bottom and one for the top. Now, that's very interesting to me because that's in effect one of the models we have, a log model for the bottom and a different log model for the top. So he arrives at the same thing completely independently because we hadn't talked to each other before this. And I found that very striking and very interesting. Just to make some comments on that, what Venkat refers to as class means the class of preferences. Whereas when we refer to class, we refer to income and property income, though it could be argued that those people have different preferences. But the issue is really where the difference is located. Secondly, he assumes perfect equalization of wages for each type of labor. So the distribution of labor income can only arise from wage differences among occupations, or what the value of the standard neoclassical theory of wage is equal to the value of your labor, the value of your margin product. We instead argue that turbulent arbitrage, which is a combination of drift and diffusion, gives rise to this exponential, near exponential distribution. And for any given type of labor, by implication, different types of labor will have the same process, but they need not have the same wage. And that therefore also applies to race, gender, and so on, which are different types of labor suffering discrimination, but are still operated on by the market in the same way. I didn't present in the paper data by occupation, but it's available, and it's strikingly consistent with this. But the last point is that the theory by which you get to the endpoint informs the interpretation. So while it is informative to know that there are differences, it's not informative in the sense of the cause of the differences. And for me, this is really fundamental because many people have observed these differences. How do you explain them? And the theory, the underlying theory, is exactly what allows you to interpret them and posit ways to test it. That's a very important point. So, summary and conclusions. Not bad. Yeah, not bad. Traditional econophysics relies on this energy conservation method. And it has many powerful tools at its reach, so to speak, and many different models that'll give you something similar to this. And then the question is, can you make up an economic story or a quasi-economic story that'll give you this result? We instead insist on coming from the idea of a classical, by the way, every economic theory says wages will be equalized if there is no obstacle, except they say it's exactly equal. And the point is here that if you take it to a more concrete level, they won't be. And it's striking to me to note that entropy maximization appears in both of those arguments, and indeed Venkat's also, but it has a different meaning. In the physics approach, stationary distributions, if you run the simulation for a long time, then you get a distribution which settles down, are derived from the assumption of entropy maximization. In our approach, we don't assume entropy maximization, we assume this process of adjustment with noise, and we can derive the final distribution, or we can just observe it and let it know, but theoretically to derive it is important. It comes from the dynamic paths of turbulent arbitrage. And that happens to be stationary distributions which are also entropy maximizing, because stationary distributions are entropy maximizing. But we do not use entropy maximization as the means to arrive at the stationary distribution. In our case, it's the result. So having that information, that technique, is not sufficient. You really need to have a theory of the, and if there's any talk I've ever given where I didn't say that, is because I was in bad shape, because I always say the same thing. So let me stop there. Juan is going to talk a little bit about the math, and then we'll turn over to Paulo.
The SDEs, we solved the Fokker-Planck equation of this, which is the solution that you get after a long time. This model 1.4 is basically the same one as one of the solutions of the wage models, which call it the log linear model. One of the nice things of this model is that it gives us the same solution as the CIR model without saying anything about how the noise is. So in this case, it's just sigma, but it gives the same solution as the CIR model, which is gamma, and that's the reason why it fits so well for the lower 97% part, which is the one which is related with wages. The coefficients with which we fitted the model we then use in the simulations, showing in this case that the simulations fit quite well with the model as well. And that's pretty much it. It's worth noting that the solution of the Fokker-Planck equation is very similar to the Maxent. The difference lies in how you see the process. You have a frequency approach in the SDE, in the sense that you take into account time, and then you take into account what happens, or where do the data points lie in each point in time. So that's sort of a frequency approach to this, which is somewhat different than the Maxent, where you don't say anything about this. So that's pretty much it about how we solve this. We go from the SDE to the Fokker-Planck equation, and from there we derive the stationary solution of the model, and then with these parameters we solve the simulations as well. That's it.
Cool. Okay, I have a set of slides that I hope to get to. This is happening very often. I think this is the third time I get up here to talk about these things. This is a very interesting and important discussion that here was initiated by Sanjay. And we have been carrying this discussion out and realizing that other people have been involved in all sorts of aspects of these discussions. Duncan is here, Ravi Kambor, and other people are trying to figure out what are the different ways in which we can draw from statistical mechanics and information theory to make progress in economic analysis. And it's not a simple question, certainly not within the discipline of economics, given a series of, the word that comes to my mind is ossifications in how many of our colleagues approach the study of economic systems. My take is kind of simple. I think that statistical mechanics and information theory give us tools to develop an observationally grounded political economy. And this is pretty exciting. It allows us to develop a political economy that's centered on results that capture the emergent social content of interactions in decentralized market economies. This is what Smith was trying to do. This is what Marx was trying to do. And we can now do it in a more robust observational basis with these tools. We can see beyond what Marx called fetishes of people acting on things. And in particular, and this would be the theme of the discussion today, it allows us to see beyond a particularly pervasive fetish, the fetish of the self-standing individual who is ontologically independent of his or her relationships with the rest of society. That informs much of contemporary economic analysis. And we can go beyond simply criticizing it. We can actually start constructing, on the basis of observation, characterizations that embody a different understanding of how we can understand, how we can approach, think of economic systems. Swinging for the stands with this one. And in particular, coming to the realization, starts with classical political economy, that the regularities upon which we can predicate an understanding of functioning of economic systems are realities, are regularities defined by collectives, groups of people, things like classes. And also, I hasten to add, things like ethnicities, race, and gender. That those actually give us indispensable traction in understanding the outcomes that we can observe. I've had a real hard time putting this talk together because I've been working on this for a while, mainly talking to myself. And there is a lot. So I will refer you to the things that are written, that are coming out in the journals finally. Papers with Ella Scharfenacker, Jang Ho Yang, and more recently Noe Wiener as well. So I'm going to focus on what I think are the most important aspects, perhaps the most distinctive, and quite likely the most controversial aspects of what I've been doing in this work. And most broadly, the point I want to get across today is the following. The strong form of individualist reductionism that informs contemporary economics is a problem. It's a problem conceptually, but perhaps even more sharply, it is a problem in terms of informing observational work. It looks like it can inform observational work, but it does so in a way that is potentially misleading. Individualist reductionism seeks to understand or frame economic reality, and in particular, including aspects of economic reality we can observe, as expressions of in relation to very detailed descriptions of individual behavior, characteristics, and mechanisms. An explanation for most of our colleagues is a reduction to some very detailed account of what people are doing and what are the mechanisms that arise as a result, very often at equilibria defined by some kind of optimizing behavior. The broadest possible problem that this poses, if you take a big step back, is that individual characteristics that are the foundations for these approaches are themselves social. They are a product of the interactions that we're seeking to understand. Preferences, technologies, the goals that animate economic agents, the manners in which they measure their well-being are all endogenous products of economic interactions. This creates some very serious difficulties. Now, let us be generous and let us be precise. Once you realize that socioeconomic life consists of a large number of individuals interacting, developing institutions, and through those interactions and institutions changing themselves, you realize that the individualist approach actually boils down to a parametrization, which is fair enough as part of the process of understanding the functioning of a system. Hey, suppose these things are constant. Then what? The difficulty, to my mind, is that it's a parametrization that is typically conservative in as much as it fails to then point inquiry toward the determinants of differences in the current state of individuals, which is often the most interesting question of economic analysis. It's also often impractical, but I'm not going to go into that very much. But I think most importantly, it's arbitrary. And I do want to dwell on this a little bit. Why it's an arbitrary parametrization. And at the broadest level, it's arbitrary because it supposes that the regularities in the systems that allow us to say something meaningful about their functioning are defined at the individual level. In other words, that the structural parameters, to use a term that has been bandied around quite a lot, in a capitalist economy are things like individual preferences, technologies, or a very stylized conceptualization of rationality. And that is, in as much as we can characterize those, that we can understand the economy as a whole. I don't think that that is quite right. I don't think that those are necessarily the structural parameters or the regularities upon which we can ground understanding. And because there's no reason to expect that in a complex system where, as I said, individuals and interactions are mutually defining, there's no reason to expect that the stability, the regularities that you could ground your understanding on are going to be defined at the level of individuals, as opposed to being defined as a result of very particular interactions between elements of agency and alertness and structural interdependencies. Now, there's a plural set of contributions in the history of political economy that points to a different approach. And it's quite a bunch. You have Anwar Shaikh, you have Gary Becker, you have Friedrich Hayek, Eugene Fama, Adam Smith. I mean, you could throw the Easter Bunny in there, right? I mean, it's people coming from very different directions, but pointing to the same thing. That, in fact, the regularities that allow us to say something meaningful about an economy are actually defined at the systemic level. In different ways, in different contexts, the devil's on the detail. This is all at a very high level of generality, but that they are irreducible to the particular details of any characteristics, knowledge, or actions of any individual. Even if you don't believe me on that one, there is a practical problem that arises from the data that is available to us. When we talk about data collection in economics, we're talking about observing things, what, annually? If we're lucky, quarterly? If we are phenomenally lucky, monthly. In an interacting system, those are too long. These gaps are too long for us to posit that what we observe is anything but a reduced form, accumulation, accretion of the results of interactions. So that in what we observe, actually a lot of the information of about the fine-grained detail of the processes that generated things has been lost. So here's where statistical mechanics and information theory are useful. And I have some slides to try and motivate why it is if I have any time left. I don't know how much time I have left. What time is it? Oh, well, we're good. I can go on. Cool. OK. Did that make some sense? It's abstract. Read the papers. Hopefully the papers help make it more concrete, specific, and the disagreements that arise can then be addressed, I think, in a more advantageous terrain. Why does information theory and statistical mechanics work for economics? Well, basically because we have the kind of system that is very much of the kind of system that prompted the original development of statistical mechanics. We have large N systems. Systems where it is, let's start with inconvenient, and we can make a bolder version of this claim later, to attempt to understand their functioning on the basis of detailed knowledge of the evolution of every single member. So we look for different ways to try and understand these systems, large N systems. Formally, what we can do is this. Suppose we have a system with n individuals where n is very large. Cool. Each individual is in an individual state. Call it big X of V, which consists of V different degrees of freedom. These are various characteristics. They can be quantitative, they can be qualitative, they can pertain to an individual, to the group as a whole, whatever you want, these can be. The beauty about mathematics is you can do whatever you want. And I'm going to do a trick. Suppose this is an exhaustive description. Good model, huh? It tells you everything that is relevant to the economic behavior and functioning of these individuals. Then, once you have that, you do a mapping that can involve some coding, certainly involve some coarse graining if the variables are continuous. And you take the total state space of individuals, all of the values of this X that each individual can take, and you divide it into little bins. Right? So that each individual at any given point in time is in a bin that fully describes their economic characteristics. Okay? And say we have SV bins. Cool. Then we have entropy is a tale of two spaces. Because it relates two spaces that are always posed when you're considering systems in the small and systems in the large. You have first a phase space of micro-level configurations taken by members across the bins. Basically, suppose we are this system, and each one of us has a state. Each one of us is going to be in a bin, right? But we could be in any one of the bins. So we can consider every possible configuration of the system, right, of each one of us across every conceivable bin. People with me? That's the micro-level configuration space or phase space, and we're going to call it omega, because that's what people do. But then something interesting starts to happen, because you realize, see, if you're interested in what's going to happen to Anwar, you would have to take care of Anwar in this system and follow his evolution. But the systemic functioning, I'm sorry, Anwar, really doesn't care very much about Anwar per se. It doesn't care about anybody. It actually cares about how many people are in each bin. Yeah? So you start realizing that, hey, there's a certain loss of information. There are certain things that start to become irrelevant to the systemic functioning of the economy. People with me? And the first step along that road is this fact that the system doesn't care who is in a bin. It just cares how many people are in a bin. And you can go further. You can say, actually, maybe if you're going to normalize everything by the system size, you don't care how many people are in any given individual state bin. You only care about the frequency or the relative occupancy of any bin. How many people make between $100,000 and $110,000 and live in the Northeast with 13 years of education with a net balance sheet position of plus $10,000? Say, and optimistic. There's some categorical coding for their happiness, optimism, or whatever, right? So you could do that. And once you do that, you realize that it is more convenient and it is possible to describe the state of the system as a frequency distribution, as a listing of the relative occupancy of each individual state bin. Very convenient. Once you do that, we're going to call that phi, V. We can understand this as obviously a space of all possible macroscopic states of the system. And as it turns out, this way of describing an economic system will give statistical expression to any irregularity that arises out of the functioning of the system. Now, entropy allows us to link these two sets to each other in a way that's really helpful. And it doesn't matter if the system is physical, social, if it's a big N system, this is going to be useful. So entropy is defined by a relationship between these two sets. And basically what it tells you is for every point in that set over there of macroscopic states, these distribution functions f, it tells you how many points in this more detailed set of individual configurations, how many of those give you that state. Right? It's a particular measure. I'll put it on, it's logarithmic and it's an average, but that's what it's measuring. We call that the multiplicity of a macroscopic state in the phase space of microconfigurations. In English, we're basically saying, look, here's a particular outcome, macroscopic outcome. How common is it across everything that can happen in the economy? And it turns out that that's very useful. Why is it useful? Well, that's measured by entropy. And just so people know, W of F is the macro state in question. W is its multiplicity in the phase space phi. And this is basically linking the combinatorial definition of entropy to the Shannon way of putting it, and they are completely equivalent. Not terribly important for our discussion right now. It's useful, entropy, because in a large N system, the state that achieves maximum entropy over a given set phi is overwhelmingly dominant over all other possible states. And the larger the N is, the stronger the overwhelming is. So, what can we do with this? Well, if we can express our knowledge or beliefs about the functioning of a system as a description of a set phi, of all the possible macro states that the system can take, then if we're right, if we believe we are right, we should expect to observe the system at the macroscopic level doing things that happen when you are at the maximum entropy state. Yes? So in a way, you can interpret this as a prediction. Hey, if these elements of my knowledge are right, the principle of maximum entropy leads me to believe that I'm going to observe macroscopic outcomes like this, with these properties and these relationships. PV equals nRT, for instance. Now, if we have beliefs and we construct a phi set, we consider the maximum entropy distribution, and then we look at the world, and the world doesn't look like the maximum entropy state, guess what? We're wrong. Our knowledge that we use to define the phi space that we started with is either incomplete or just wrong. So rinse, repeat, right? The point here that I'm trying to emphasize is that the principle of maximum entropy then is simply a heuristic, a tool. It's not a behavioral hypothesis. It's just a way that allows us, in a logically robust manner, to link knowledge about micro-level and macro-level states in a system. And it's grounded, fundamentally, on very simple combinatorial considerations that follow from this aspect of anonymity, that up until an exhaustive description of the individual state of a particle, of a person, people are completely interchangeable. Yeah? I should say members, because I'm about to say that we can't really do this in economics like that. But people cool? Okay. It's interesting to note here that there's a very different way of thinking about the relationship between micro and macro in all of this. There's no representative agent here. And also, there isn't just making statements about macroscopic relationships. What there is the understanding that basically we should expect to observe at the macroscopic level that which is most common if our knowledge at the micro level is true. It's just making that statement for a particular abstraction with this coarse graining, these phase spaces, and all of that happy stuff. In thermodynamics, people did this, and they were able to link then fundamental principles of physics like the conservation of energy, like the conservation of momenta, to relationships at the macroscopic level that they understood from before, from the lab, because they measured it. Relationships between macroscopic characteristics of gas systems. And they were able to link that to very simple things, i.e. the conservation of energy. And there's an important point here that goes to some differences that arise within physics and I think are arising within economics in the application of these methods, which is this. When the physicists did this, going from knowledge of energy conservation to maximum entropy characterizations of states that then yielded macroscopic relationships that were in line with what they were observing in laboratories, what Gibbs concluded, at least according to James, was that the macroscopic relations then were nothing but systemic expressions of the conservation of energy and the conservation of momentum. And the reason that needs to be stated, and it's going to start sounding like economics in a second, or the controversies in economics in a second, because Boltzmann had a different approach and different understanding. He basically wanted to understand the macroscopic relations as the result of the detailed evolution of the individual particles. And spent quite a bit of time actually deriving the equilibrium steady states in relation to all sorts of models of interaction, collisions, and so on and so forth. Jaynes argues that the problem is that Gibbs died before he could finish his book. Okay? But Jaynes argues that Gibbs was actually charting a fundamentally different path. That all of this works not because it's an apt description of the detailed microkinetic interactions and evolutions of the individual particles. It worked in physics because energy conservation is true. In other words, the only truth content of the macroscopic relations is the conservation of energy in that particular ensemble. I mean, there's other applications, obviously. Yeah? Now, of course, in social systems, we encounter a different problem. I will race through this. What time is it, Anwar, sir?
30 minutes.
OK. OK. I have, I think, this slide and another one. All right. So we can't observe the full state, the full vector of individual states. That's the first problem. Second problem, we don't even know what the full vector is. Right? We observe things at certain frequencies. We don't know what the laws and regularities of the system are. In fact, some people even say there aren't any regularities. But there's something that we can do. We can basically apply what the physicists did with Boltzmann, not Maxwell, Boltzmann and Gibbs, the other way around. And basically look at frequency histograms that we can construct on the basis of observation to make inferences about systemic regularities. And there are two settings. And I'm just going to talk about this, and then the other one, I'll just point people to the other work. Sometimes the histograms we construct can be well described by closed form functions that we know and love. And often these are closed form functions that we know are entropy maximizers over fairly easy spaces phi that we can characterize, typically with moment constraints. If that is true, it is possible, I'm not saying best, I'm saying possible, to construct economically meaning theories that are capable of generating these macroscopic constraints that may give us some insight into the emergent social content of these atomized interactions that are generating this data. And the two examples where I've sought to make an intervention, and I'll close with this, involve the idea of social scaling and the paper I presented here last time. I'm not going to say anything about the paper I presented last time except to say that we can interpret distributions of returns on capital as the result of a maximization of profit in the presence of certain costs. That as an emergent feature of the process of capital mobility that Smith, Marx, Anwar, Duncan, and many others have emphasized. The idea of social scaling arises out of a wish to engage with these implied first moment constraints that are present in a lot of distributions we observe, and out of a similar dislike of the explanation based on conservation of something, right? And the basic idea is that you can actually, there's a class of economic processes that can generate the zero-sum interactions that appear as first moment constraints that are defined by the possibility that some outcomes of complex patterns of competition boil down to a basic scaling of certain individual characteristics by social measures of themselves. And if that is true, there are certain conditions under which some variables are going to be subject to first moment constraints, not as an expression of conservation, but as an expression of the irreducibly social referential content of the outcomes of competition in markets. And the last thing, plug, there's this work with Noé Wiener that's coming out where we're using these tools for an instance where closed form solutions are not available, but we can still use information theory and the combinatorial content of entropy to identified the systemic relevance of things like race, gender, and ethnicity on distributions of income. And it's fairly interesting stuff's coming out of that. And on that note, I will shut up. Thank you.
So thank you all for coming out. I'm really very glad that we're having this discussion. As you know, this is the second of two discussions on the theme, one of which was in the fall. And I'm very glad that Venkat Subramaniam from the Columbia Engineering Department is also here, since he presented his work on the issue earlier too, to great interest in our department. As Paulo mentioned, in some sense this series of seminars began as a result of my own wish to gain greater clarity as to what is the applicability, if any, of a statistical mechanics approach in the social sciences. And I should say that I approach this with sympathy. After all, I am a student of Isaac Asimov and the Foundation trilogy, which features psychohistory, as I mentioned last time round. I'll mention it again, which is imagined future social science, which uses statistical regularities to uncannily predict what is going to happen. But at the same time, I find myself very dissatisfied still with the idea of explanation, which I think is being presented in this way of approaching social science. And that's really my preoccupation here. What is an explanation in the social sciences? What should count as one for our purposes? And when should we privilege a specific methodology as providing what we take to be a satisfactory or a more satisfactory explanation than another? And in a nutshell, to my mind, I don't believe that that question has yet been answered in a way that is fully convincing. So I'm going to give you a few reasons, at least one, I hope, that reflect my own thinking about this, at least to date. And of course, I'm willing to be convinced, and I very often am convinced by my distinguished and eloquent colleagues. So no doubt I will eventually be convinced. So you can take this as these are the turbulent dynamics on the way to some steady state, harmonious steady state. Exactly. So here's one suggestion, okay, which troubles me. And that is that life itself, not to mention economic and social institutions, the built environment in which we are present at this moment, are examples of what might be thought of as local entropy reduction. So far from reflecting entropy maximization, all of this, all the explananda, the things we're trying to explain, simply would not exist were it not for the fact that there was entropy reduction. Not entropy maximization, but variance from entropy maximization. So from that very fundamental viewpoint, entropy maximization can't explain anything, because we would just be in a gas. Everything would be a gas. I'm being simple-minded here, and Venkat and others, Anwar, who's a former astrophysicist, Duncan, who's well-versed in physics, will no doubt generate a more nuanced representation of these issues than I'm able to provide. But that seems to me to be a very fundamental question. Now, one answer to that is that one has to identify relevant constraints. And within that context, after having identified relevant constraints, one can then apply the entropy maximization principle in order to arrive at a most plausible outcome. For example, understood as a specific distribution, which is most likely. But of course, there is a mapping, to use the word that Paulo used in a slightly different context, from the specific assumptions we make as to what the constraints are to the specific conclusions we derive. And that, of course, then generates the problem that we have to identify assumptions that we think of as being plausible. So, for example, to go back to Anwar's paper, we can ask the question, is an additive or a multiplicative process more reasonable to assume? Or perhaps they're both reasonable to assume because of the salience of a two-class explanation to understanding capitalism, as Anwar, I think, might argue. Now, that is a judgment concerning salience. It's a judgment I happen to find very plausible in that particular case, but it is a judgment involving salience. Right? So I want to make that rather simple-minded and elementary point that there is judgment involved. You know, this isn't simply a machine that one can adopt, one can apply to any set of circumstances and get an answer. And that judgment involves what are the plausible or reasonable assumptions that characterize a particular case. And of course, once we recognize that, then we immediately also see that there's a language game, so to speak, that's set in train, and a specific kind of exercise for the epistemic community at hand of having a debate as to what are the most plausible or reasonable assumptions to apply in understanding a specific case. Now, Anwar and others have pointed to, I used the word uncanny already, let me use it again. There's more Marx than Freud in this room usually, but let me use the phrase or the word uncanny. Marx has, not Marx, Anwar, our Marx, has pointed to the uncanny ability of particular assumptions to, in effect, fit the data in a way that is rarely seen in economic or social contexts. Now, I agree that this is something which is significant, but my worry from the standpoint of explanation is that we might be being engaged in a sophisticated kind of a curve-fitting exercise in which what we are doing, in effect, given the data, is trying to identify a set of assumptions concerning the relevant constraints such that we can then apply the machine of entropy maximization to give rise to an answer that fits those particular data especially well. Okay. So the search in the state space of possible sets of assumptions becomes governed by our interest in fitting the data. And lo and behold, we find that there is some set of assumptions that does so especially well. Now, what does that actually validate, if so? From one point of view, it validates entropy maximization as a general methodology for doing social science because of this astonishing correspondence. Right? But another perspective would be, perhaps, that a particular narrative, a particular way of interpreting or understanding the economic and social order has proved to be one that is generative of results that are coherent with our world, perhaps because that narrative does indeed capture deep-seated causal facts about the world, such as that some people have capital to which a multiplicative process applies, and other people have only wage income, to which in some sense an additive process applies. Now, that seems to me a fairly parsimonious theory of the world. I might be willing to sign on to that. But my signing on to that does not necessarily mean that I have to sign on to the idea that entropy maximization provides the methodology to end all methodologies, or if you don't want to go that far, a particularly powerful methodology for interpreting or understanding economic and social life that ought to be privileged in a broader range of cases. Now, what do I think is left out? I think that social scientific explanation at large does concern itself with history, institutions, politics, culture, agency, collective and individual. All of these things are important to determining what happens, to what local entropy reduction takes place, to what become the assumptions that are most salient to apply in a particular context. So if we live in a capitalist system in which the additive and multiplicative two-class dynamics, which I just described and which Anwar described, hold, that's the product of a specific process. And Anwar, of course, would himself not deny that, involving history and politics that has given birth to that. So what we have instead of a general methodology is one that happens when suitable assumptions are chosen, which applies to a particular context because of the specific histories that gave rise to it, to fit it well. Okay. I was talking with Ravi Kanbur on the weekend about this issue, and we talked about the example of economic geography. That one of the findings of economic geography, of course, a la Paul Krugman, but also others, including Alfred Marshall, is the idea that it can be arbitrary where industries locate, or indeed where cities arise. Because following a physical metaphor of the formation of a crystal, right, you need to have a nucleation site, some particular point of origin, some particular initial condition which sets off a process in order for an agglomeration economy to emerge, the increasing returns to scale that constitute urban formation to be present. But that can happen in an arbitrary way. A city can be located here or it can be located there, right? The United States perhaps could have been the machine tool exporter and Germany could have been the airplane exporter, but it's the other way around, right? Now, it seems to me that there is very little way for us to think about such path-dependent processes which are ubiquitous in economic and social life without avoiding without confronting the facts of history in all of their complexity. I gave the example of a crystal, which is something that doesn't have agency, but of course once we introduce human agency into the process, then it becomes a territory of explanation which is much more specific to economic and social life and which requires other things of us. So perhaps I could just say something about what I consider to be good in this turn in our department and in general. I think that one of the things that's good about it is the focus on distributions rather than on individual level maximization. And what's also good about it is that that focus on distributions therefore permits many different understandings of the causal processes that give rise to those distributions. Venkat actually has in his book a causal process which does involve individual level, so to speak, rational decision making, the intentional pursuit of an objective. Anwar and Juan have not committed themselves to any specific account of the individual motivations which underlie the drift diffusion processes which they have in mind. So there is the possibility of entertaining many different explanations as to how and why it is that a distribution might emerge and might enjoy stability in a specific case. And I think that that's a very powerful and attractive feature of this turn, in part because it avoids what Paulo called, I think, reductive individualism. Sorry, individualist reductionism, but it could have just as well, perhaps, have been the other way around. But that doesn't, it seems to me, resolve the most basic problem, or the more basic problem, of how and when it is that we arrive at certain assumptions rather than others as a prelude to applying the entropy maximization methodology at all, or indeed a specific account of the arbitrage processes, the Fokker-Planck equation which characterizes the drift diffusion dynamics, which is actually present. Let me move toward ending by noting that Paulo's, I think, representation of why we should adopt this methodology is that in some sense we are obliged to do so once we have laid out our assumptions and accepted that those assumptions fully characterize what it is that we know, and that all that remains otherwise is ignorance. So his view, as I understand it, is that if that's so, if all that remains otherwise is well, what remains is that which we cannot speak of in any specific way, then we have no choice but to assume the interchangeability of the agents. He will comment in response to me, no doubt, or we have to recognize that we're at the limits of our knowledge, and in that context, entropy maximization becomes a reasonable principle to adopt. But I would ask, how do we arrive at the particular characterization of what we know? And what is the backstory, so to speak, involved in that? And I think that that's where all of the economic and social elements of economic and social explanation that I've mentioned, history, politics, norms, and so on and so forth, are inescapably present. So I suppose the methodological challenge to you would be to ask whether you would have to, or whether you would be willing to accept a rather more delimited, right, rather more confined account of what is the proper scope of the entropy maximization approach. Thank you.
Okay, well, I would also like to echo Sanjay's appreciation for having these two presentations, and I think I at least learn a huge amount from this discussion, and it's invaluable in that respect. I'd also like to say that the back story of these presentations, that is the discussion of these methodological and philosophical questions in the department and in emails and stuff like that behind the scenes of this, have been hugely helpful to me in clarifying questions and making me think more clearly and articulate my own thoughts about this. So it's really a privilege to be part of this process at this in this juncture. My main theme today is really to try to argue that there's not quite as much new in the statistical mechanical approach as it might seem at first, and that a considerable amount of what people perceive as novel or unfamiliar really comes from the fact that the language is rather different and the perspective is rather different, and not so much because the substance of the issues, say, of explanation, as Sanjay raised it, are completely different. So let me start from Paulo's point. One feature of the statistical mechanical way of thinking about complex systems is that you start by describing the system in terms of a probability distribution over the state space as he outlined it. Now, I'd like to start by saying, is that really so different from conventional economic and other ideas? Well, it isn't that different, but it looks a little different for the following reason. For many, many years, economists didn't have any data, or if they did have data, they barely had any
way of using the data, because there, until the 1970s or 1980s, there weren't data processing machines available to do much with. But the statistical physical point of view is not so different. It's also trying to distinguish central tendencies from fluctuations, but it starts from the other end, and it says, let's not think about the shot in the dark, let's think about the general configuration of the joint probability distributions that can describe the system in the sense that Paulo outlined. Now, why do you maximize entropy? In that, so you maximize entropy. Now, I'd like to emphasize another point that really hasn't been brought out completely, but it's implicit in Sanjay's remarks. The way, Sanjay's exactly right. That understanding explanation of social systems is to understand why it doesn't have maximum entropy, why it isn't a completely random gas-like system. And the formal answer to that, which we haven't used this term yet today, I don't think, is constraints. That is, that you maximize entropy, but subject to certain constraints, and those constraints represent the institutional and behavioral regularities that you think of. Paulo mentioned this indirectly, talking about conservation laws, conservation of energy and momentum. But in the social science context, Sanjay's exactly right. When you constrain the system, you're going to reduce its entropy. Either the constraint doesn't make any difference, in which case you don't reduce the entropy, but if the constraint does make a difference, it's got to reduce the entropy, and that's in the formal way in which this approach introduces exactly those points that Sanjay was mentioning. And there's no way that maximum entropy by itself can predict history. That's also true. You just have to assume that if you're going to have institutions like private property or capitalist production giving rise to things like rates of profit or wage rates and so forth, that's just part of the history that led up to where you are. Why do you maximize entropy? Well, there is a good reason for maximizing entropy, and it's also against the shot in the dark approach. It's because statistical physicists understood that random does not mean normally distributed or uniformly distributed in general. What it in general means is maximum entropy subject to constraints. That's what random means. So, and another way to put this point is to say that you use maximum entropy. You can read about this in Amos Golan's book, or in Jane's is very eloquent on this. The reason that you do use maximum entropy is to avoid implicitly bringing into the analysis assumptions that you're not making explicit. So you want all the assumptions to be explicit in the form of specific constraints. Having said those things, I'd just like to underline the first point that I made. Many of the philosophical and explanatory issues in maximum entropy modeling, or what is formally very equivalent, say the drift diffusion derivation of these results. All of those problems tend to be problems that you get in any kind of explanation based on equilibrium thinking. And we know equilibrium thinking is very tricky. That's one of the lessons that we learn from economics, even from the very elementary discussion of movements along the curve and movements of curves in, let's say, supply and demand models and things like that. What is it that is the cause of the price and quantity that you see in a supply and demand model? Well, it's both the supply curve and the demand curve, right? I mean, you can't, and if you start trying to do counterfactuals or comparative statics, you know that you don't get a determinate result unless you tell which curve is shifting and what kind of shock you have and all of those points. Well, that kind of philosophical problem about explanation is not really qualitatively different in the statistical point of view, because the statistical models lead to equilibrium. There's maybe a good argument against framing explanation in terms of equilibrium. You might much prefer to frame it in terms of explicit dynamics. But Paulo explained just why that is so very, very difficult in with social phenomenon, because we have both very large numbers of degrees of freedom and extremely limited data resolution in order to recover local dynamics. So it turns out in the history of economics, it's quite a pattern that the same ideas, when they're posed in equilibrium terms, have much more influence than when they are posed in dynamic terms. One outstanding example of that keeps coming up for me is that Keynes wrote his treatise on money in dynamic terms. So the presentation of the ideas in the treatise on money is that it's disequilibrium, and it's the movement of variables in order to reach an equilibrium that's the centerpiece of that. When he put many of the same ideas into the general theory context as an equilibrium model, all of a sudden economics was, at least for a period, revolutionized, and people could had much more influence. So I think those are the main points that I wanted to make, and we could move on to discussion. I don't know, Adam, how do you want to? I should keep it on? Just leave it on the table. Okay. Shall I be the moderator here? Comments and questions? It all became as clear as mud, obviously.
Everybody agrees with me now. So.
Everybody agreed with everybody. That was amazing. Anwar.
I think this has been a very useful and illuminating discussion. And for me, what Duncan said about the prior, the assumption that you come in, is what I understand to be what theory gives you. I don't think the idea, for instance, that labor migrates towards higher wage areas is just from my personal observation, right? People like Smith and Ricardo and Marx observing a use capitalism which allows this because you're not tied to the land, and they're very clear about this, specific to some social historical conditions, and it has many impediments. They all talk about that. So that part is, to me, groundwork. It's like recognizing that there is gravity or there are planets. But then the specificity of that, one has to be careful about. I specifically focused on advanced countries for good reason, because you can't easily apply this, obviously, the transition to capitalism, even in development, or even in many areas of an advanced country. So I specifically focused on large patterns, aggregate patterns. I wouldn't want to argue that every state has. But let me remind you that Trump's caravan is a reflection of this same gravitational pull, in spite of a huge number of walls that were imposed on it. So the pull is there. Its form depends on knowing more about the specific historical and social conditions. So I think there's not that much difference, I think, from that point of view, except that for me, it's never grounded in the individual. it's not the internal reflection of what I would do. That's not relevant because we're observing a social system. We want to know what it does. So that's the difference for me where theory comes from.
Marjan. I think you want to speak up very loudly because if it's going to pick up in the mic, it's going to.
I have two questions. They are related, and I might be wrong in the way that I grasp stuff. So please correct me if I'm wrong. So the main problem that I have with this aggregation method in the statistical mechanics, and particularly entropy maximization. One question that I have is that it seems to me that we are relying on this story that in a complex system, interactions are more like an arbitrage type all the time that are negative feedback. And so my question is that whether they are able to embrace the crisis-inducing and entropy increasing result of interaction as well, what can lead to bubble formation, for example, and reflexivity problem that Soros talks about. So my argument is that interaction of individual in a complex system can have both positive and negative feedback. And then as a result of both of this, we can have stabilizing and also destabilizing forces. So statistical mechanics and entropy, I mean, generally focusing on aggregation power can tell us that, yeah, we cannot get to explain the macro state fully from the micro state, so there should be the linking process, but the direction of the macro is not very clear only by aggregation. So like the trends that we are like the regular patterns that we see through history, how can we explain them without other things such as power and institutions? And then my point about institution, I understand that in concert that we are doing entropy maximization, we can enter institutions, especially like informal institutions like Paulo did in social scaling. But I think sometimes institutions work like super agents, that they also have interactions. So sometimes there are institutions as if they have their will of their own and they do not add to the process and to the aggregation. So they are like super agents that they are not static, they are dynamic and they change, but there is also interaction.
Paulo, did you want to respond to that? I have a little response. You have a question, Mark?
Yeah, I was just going to.
Well, yeah, let's do that because we're getting close to the witching hour here.
So I was just going to ask, very, very generally, if the techniques that we're looking at encourage us to think in terms of distributions, and at least encourage us to think of distributions rooted in the data rather than a priori assumptions, do they not nevertheless then rule out very little by way of explanations of outcomes, and rule in really still quite a lot of explanations, leaving the majority of the process of explanation and distinguishing between explanations still a job that needs to be done.
Maybe one more. Duncan.
If I may, first of all, thank you very much for inviting me to attend this. I've really benefited and found the discussion to be really interesting. It's somewhat of a comment about what Paulo said, that the emphasis shifting from individual aspects to systemic effects in the maximum perspective. But in statistical mechanics, entropy is the bridge to go from micro to macro. I mean, where we do have models of how individual molecules behave. We can write down the so-called Leonard-Jones potential interactions, and from which we can use the statistical mechanics machinery to predict macroscopic properties such as pressure, volume, temperature, and a whole bunch of other things. So there is a way to go from micro to macro. Why can't we do that in economics?
You want to?
I'm jumping at the bit here.
Okay,
This-
why don't you champ it?
This is a perfect question, and you're absolutely right. When James was talking about the differences between Gibbs's emphasis on the macroscopic relations, effectively being emergent expressions of simple things, versus Boltzmann giving you the detailed microkinetic description, he said, obviously, the microkinetics are true. Boltzmann got it right. The difference for us in the economic system is that, unlike in physics, we don't know 1/2 mv squared. Right? We do not know what the conservation principles are. We have certain ideas. We know, for example, that they are income expenditure identities, right? And that rules out a lot of the phase space and so on. And the difficulty, I think, Duncan, you really nailed it, on this contrasting of the shot in the dark versus the observation and to think about it. The discipline gravitated towards basically making assertions. Oh, suppose the microkinetics are this. And not only that, then tending toward a general approach to observational inquiry, where in as much as the observation failed to match the theory, the observation was wrong. There's a real scientific problem in our discipline that has developed. So a lot of us are coming from that, not as we don't want to reject the fact that ultimately there are microkinetics, and certainly in chemical systems and in physical systems, we actually know the laws of motion. We're simply saying that they are infinitely more complicated, and yes, I like the way that you put it, that the observational set is incredibly sparse for us. So that's not the thing. The other thing that touches on, again, very important points made by the way I see this, I have a bit of an opportunist approach to the use of these methods. I'm not advancing this as a panacea. In fact, before I engaged with this, all of the empirical work I did was looking at balance sheets and corporate reports and things like that. Ask people what they're doing economically. It is simply the following, that when over a certain time period in a certain institutional setting, there is stability, distributional stability in something for which you would expect no stability, that's telling you something. That is not to say that that stability will remain forever. A self-organizing system like our bodies will eventually thermalize into oblivion. There's a happy thought for the day. Yes? And that is true. Does that mean that we cannot characterize the process of self-organization? Right? But you're absolutely right. And I think that part of what people are coming from a little bit is an aversion to the bad habits of the discipline in terms of the elevation of certain methodological toolkits into a canon. And I think we should be more like the geologists. Hey, here's something to explain. Let's try. And in that sense, the interventions are much welcome. And in particular, to make the point again, the point about the irreducible theoretical content of the priors. And when I started my little spiel about where I'm coming from, I think every economist needs to start with that. I am trying to make a case for X. Go.
I'd just like to say one short word about Marjan's question, which those are really good questions. But don't you think some power relations, well, first of all, within entropy is not always averaging. Entropy can push you to extremes if, for example, there are positive feedbacks of the kind you're talking about, say strategic complementarity in the underlying game or the underlying interaction that you're looking at. And it's often the case that power relationships seem to be a very strong equilibrium. It's because everybody accepts them and doesn't see any way as individuals to get around them that the power relation sustains itself and reproduces itself. Now, that's not all power relations. I mean, probably if you tried to do Genghis Khan or something, an equilibrium model isn't going to work very well because Genghis Khan exploded across the Mongolian steppes in a few years, and that wasn't a very stable thing, and that was highly historical. But so that's not the kind of thing that you're trying to deal with. But if you're trying to deal with the hammerlock that, let's say, American capital has over the American political system, isn't that an equilibrium? Doesn't that have a kind of equilibrium flavor to it? So, thank you. Do you want to say one more word? I guess
Just a
1 minute.
brief comment is that it's too easy to pose ourselves in opposition to neoclassical economics, which we agree is a very bad foundation and too easy, therefore. My understanding of what the classical tradition meant by laws of political economy is that there are processes that override intentions and they create the structural patterns. And that means that when capitalists move to some place to get a higher profit rate, they will not necessarily get a higher profit rate than the average, and the movement creates the opposite. It creates the negation of the intent, and the same thing for wages. Class struggle, for instance, struggle among workers and capitalism, among workers and so on, is also disciplined by the same notion of competition. Because you can't just do everything. There are consequences for doing that. And other things like international trade, finance, interest rates, all the kinds of things I tried to establish in my book, are patterns created by these fundamental gravitational fields. It does not imply that you can explain everything. The whole point is that you can't explain many things by this, but you can explain quite a few. And if you don't keep those in mind, you will misread the others. That's a key point for me. You'll misread the others.
Okay. Thank you, everybody.